I'm Mark Varenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 5. Find the smallest positive number that is evenly divisible by all of the numbers from 1 to 20. Immediately, we can find one example of a number divisible by every value from 1 to 20, namely, the product of all the numbers from 1 to 20. This is a common multiple of all of these numbers, but the value we want is actually the least common multiple. Fortunately, the least common multiple, or LCM, is a well-studied and well-understood mathematical function. First, we're going to talk about its companion function, the greatest common divisor, or GCD. GCD is a very old mathematical function, with references to it appearing as early as Euclid's works around 300 BC. The GCD is a function which takes two positive integers and returns a positive integer. As the name implies, GCD will return the largest positive integer which divides evenly into both of its inputs. Let's see a few examples. First, the simplest case. If the two numbers are the same, then the result will be equal to the inputs. Clearly, 7 divides into both 7 and 7, and any larger number will necessarily be too big to divide evenly into either input. Now, for something a bit less trivial. What is the GCD of 10 and 14? Well, the divisors of 10 are 1, 2, 5, and 10. The divisors of 14 are 1, 2, 7, and 14. The common divisors are 1 and 2, so the greatest common divisor is 2. Enumerating all of the divisors will work, but it's a bit of a tedious process, especially if the numbers are large. Fortunately, in Euclid's works, he describes a method of calculating the GCD efficiently. To calculate the GCD of two numbers a and b, first, we note that we can always write a as b times some quotient plus a remainder term. This is called Euclidean division. This asks the question, how many times can b go into a evenly, and what's left at the end? Our R1 term is always going to be smaller than b. If it was larger, then b could have gone into a one more time. Now, once we've done this, we're going to take b and R1 and do the same thing. R1 is smaller than b because of the previous step, and R2 will be smaller than R1 for the same reason. So, if we keep doing this, our numbers are going to keep getting smaller. Eventually, we'll hit a point where the remainder term is 0. When we hit that point, we can stop. The final non-zero remainder is our GCD. Let's see a more concrete example of this. For this example, we'll use 10 and 14 from earlier. First, we write 10 as a multiple of 14 and some remainder using Euclidean division. This is a bit silly since clearly 14 does not go into 10 even once, but it still works. Now we take 14 and 10 in the other order and do the same thing. 10 goes into 14 once with a remainder of 4, so our new remainder is 4. Now we're working with 10 and 4. 4 goes into 10 twice with a remainder of 2. So our new remainder is 2. 2 goes evenly into 4, so we get a 0 remainder term. Our last non-zero remainder was 2, so our GCD is 2, which agrees with our earlier assessment. Let's take a look at why this works. Let's assume, for the sake of argument, that our entire Euclidean GCD algorithm took 6 steps. In this example, once we did our 6th iteration, we got a remainder of 0, so R5 is our GCD. First, we want to show that R5 is a common divisor. That is, that it divides evenly into both A and B. Clearly, R5 divides into R4, since R4 is written as a product of R5 with something else. Now, we know R5 divides R3 since it divides R4 and trivially itself, and R3 is the sum of a multiple of R4 and of R5. Likewise, we know R5 divides R2, since it divides R4 and R3, and so on. We follow the chain of logic up, and when we get to the top rows, we find R5 must divide both A and B. So R5 is a common divisor of A and B. Now, we want to demonstrate that it's the greatest common divisor. Let C be a common divisor of A and B. Then we'll start at the top this time. C divides A and C divides B, so C must divide R1, which is the difference of A and a multiple of B. From the next line, we know C divides B and R1, so it must divide the difference, which is R2. We can follow that logic all the way down and conclude that C must divide R5. So any common divisor of A and B must divide R5. Thus, R5 is the greatest common divisor. Concretely, we can write this algorithm very compactly in a language like Python as follows. Note that we never actually use the quotient terms in our result, only the remainders. So all we need to do at each step is calculate the remainder and shuffle a few variables around. At each iteration, set A to the previous B, and set B to the remainder of the two prior values. When b, the remainder, finally hits 0, we exit our loop and return a, the last non-zero remainder. We can also calculate the GCD of several numbers by simply applying GCD to the first two, and then to the next, and so on. This is an example of a fold operation which is common in functional programming. We can write that in Python as follows. Now, I have some bad news. We're not going to be using this algorithm today. This is a very handy algorithm to have under your tool belt, and it's invaluable in later Project Euler challenges. But we need something slightly different for today. For today, we're going to look at some properties of GCD and subsequently LCM. We'll use those properties to find a trick for calculating the LCM of a collection of numbers efficiently. We've discussed prime numbers in a previous video. A prime number is a number whose only divisors are 1 and itself. We've also briefly mentioned the so-called fundamental theorem of arithmetic, which states that every positive number can be written uniquely as a product of prime numbers. The fundamental theorem of arithmetic, in effect, tells us that prime numbers are the fundamental building blocks of all numbers, and that prime numbers tell us something about divisibility. So it's natural to ask if we could use this information to calculate the greatest common divisor. And it turns out we can. Let's go back to our GCD of 10 and 14 example. If we write 10 and 14 as the product of primes, we find that 10 is 2 times 5, and 14 is 2 times 7. We can calculate the GCD of the two numbers by taking the product of all of the common prime factors. 10 and 14 only have one prime factor in common, 2, so the GCD is 2. Consider, say, 24 and 36. We can write them as 24 is 2 times 2 times 2 times 3, and 36 is 2 times 2 times 3 times 3. These numbers, written as products of primes, have a pair of 2's and a single 3 in common. So the GCD of 24 and 36 is 2 times 2 times 3, or 12. We could verify that by hand with Euclid's algorithm, but I'll leave that as an exercise to the viewer. This operation of take all of the common elements is called an intersection, specifically, in our case, a multiset intersection. A multiset is an unordered collection of values where duplicates are permitted. Now for the LCM, or least common multiple. With GCD, we wanted to take the biggest possible number that could still divide into the two inputs. So we took all of the prime factors that the two numbers had in common and multiplied them. For LCM, we want the smallest number that both inputs evenly divide into. So we want to take all the prime factors from both numbers. But if a prime factor appears in both inputs, we only need to count it once. Let's use our 24 and 36 example again. First, we pair off all of the duplicates, just like we did for GCD. These are the numbers we only need to count once. Once we've done that, we take all of our stragglers. The numbers that are left over after pairing are a 2 from 24 and a 3 from 36. Multiply all of these numbers together, and we have our LCM. The first three numbers are the primes we have in common, which is also how we'd calculate the GCD. The last two are the values that remain in order to get a multiple. If we consider our prime factorization as a multiset again, this operation is called a multiset union. We take all the elements that the two multisets have in common, plus all of the stragglers that appear in one but not the other. Note that this is different than simply taking all of the elements of both unconditionally. In fact, the latter operation will result in the product of the two numbers. Simply multiplying all the prime factors of both together is the same as multiplying both numbers together in the first place. This leads to an interesting result. To calculate the GCD, we take one copy of each value that's duplicated across the inputs. To calculate the LCM, we take one copy of each value that's duplicated, and all the values that are not. So, to calculate the GCD and the LCM together, we took every factor exactly once. Taking every factor once is the same as multiplying the two numbers, so we have the result: the GCD of two numbers times the LCM of two numbers is equal to the product of the two numbers. Now, like with GCD, we can generalize the LCM to work over an arbitrary number of values by simply folding over the list. All of this is to say that the number we're looking for is simply this. Let's write some code. We're going to use Raku for our draft, for the simple reason that Raku comes with a multiset type built in, so it saves us the trouble of messing with low-level data structures directly. Raku began its life in 2015 as the newest version of the Perl programming language. But as time went on, the developers realized the language was a significant enough departure from Perl that it should be considered a distinct language. Raku behaves a lot like traditional scripting languages such as Python and Ruby. It has functions, classes, conditionals, loops, and all the things we've come to know and love. but it also has an incredibly powerful parsing engine inspired by Perl's regular expression syntax. Let's write some code. First, a function to get all prime factors of a number, including multiplicity. This is mostly going to be a translation of our C++ code from a couple weeks ago, so I won't dwell on it too much except to point out the differences. Rather than accumulating the factors together in an ordered list as we'd done before, we're adding them together into a bag hash. Bag is Raku's word for multiset, and a bag hash is the mutable variant. So bag hash can be read as mutable multiset. Aside from that, Raku is like Ruby in that the last statement in a subroutine is returned automatically, so we don't need to use the return keyword. Finally, arguments in Raku are read-only by default, which leaves the Raku engine free to perform more optimizations of function calls. Since our algorithm needs to mutate the argument, we mark it with the phrase isCopy to force Raku to make a copy of the argument and pass that copy by value. Now for our LCM. Our LCM function takes a variable number of arguments. The star indicates that it's a variable number of arguments, similar to Python. The variable we're storing these arguments in is called @values. The @ sign is part of the variable name and indicates the variable stores a list-like object. Inside our function, we get the prime factors of each number. Then we take the union of all of the bag hashes. The union in Raku can be written using the Unicode union symbol or the vertical bar on your keyboard. By enclosing a binary operator in square brackets, we convert it to a function that reduces over a list. The variable factors now stores our multiset of prime factors. To convert that to a list, we call kxxv on it. The name of this function might seem bonkers, but it actually makes some amount of sense. Internally, a bag hash is stored as a key-value mapping, where the keys are the unique elements of the multiset and the values are the weights, or number of times the element appears in the multiset. Using this representation allows operations like the union and intersection of multisets to be much more efficient. XX is an operator in Ruby which takes a list and repeats it some number of times. So kxxv reads as take each key and repeat it some number of times based on its weight. Finally, we fold the multiplication operator over our list to get our product. To call it, we apply it to a range of elements from 2 to 20 inclusive. This is going to be our approach. Find all prime factors, take a multiset union, and multiply the resulting collection together. Now, let's learn about Jelly. Jelly is a tacit golfing language heavily inspired by J and APL. As such, there's a heavy emphasis on writing short, snappy programs to get a job done, and on being able to combine operators in neat ways without the need to explicitly mention the arguments. Like J, Jelly operators will usually broadcast over arrays. So, for example, if we add the list 1, 2, 3 to the number 4, we get the list 5, 6, 7. Also like J, Jelly operators are divided into different categories depending on how many and what kind of arguments they take. Operators which take one argument are called monads, those which take two are called dyads. Jelly also has a concept of nilads, operators which take no arguments but still produce a result. Finally, there are some special forms of syntax in Jelly called quicks, which have unique parsing rules not captured in the usual nilad-monad-dyad distinction. When we were working in J, we learned about the concept of trains of verbs. In J, broadly speaking, there are two kinds of trains of verbs, hooks and forks. We talked about forks in a previous video. Jelly takes the concept of J's trains to the next level. In Jelly, a chain of operators can have vastly different behavior depending on how it's used, how many arguments it's given, and exactly what the sequence looks like. We don't have time to go through all of the patterns, except to say that they capture most ways you could reasonably compose functions of 0, 1, or 2 arguments. And to say there's an excellent tutorial on the Jelly GitHub page, which details the exact rules for how a chain is evaluated. A Jelly program consists of multiple lines of code. Each line constitutes effectively a function. And the final line is automatically considered the main function. The main function is passed any input parameters, such as from the command line, and will be treated as a nilad, monad, or dyad, depending on the number of input arguments from the command line. In our case, we simply want to run a computation, and we require no input. We also won't need any helper functions, so our Jelly program will be a one-line niladic chain. Like in many golfing languages, the output of your program is the result of the main statement, so the result of our main chain will automatically be displayed to the screen. A niladic chain in Jelly consists of a nilad followed by a monadic chain. The monadic chain will be evaluated with the nilad as its only argument. For example, 8 is the nilad which, appropriately, returns the number 8. H is a monad which halves its only argument. This is a niladic chain which evaluates the monad H at the input 8. So it will return 4, which is 8 halved. This program will evaluate the monadic chain HH, which consists of the monad H twice. When this chain runs, it will have the number 8, our input nilad, twice, producing 2. Note that whereas in J, most verbs are overloaded and can be used either monadically or dyadically, in Jelly, every operator has a unique arity and can only be used with that many arguments. This allows us to do some more sophisticated pattern matching based on the arity of the operators we're using. A monadic chain consists of a sequence of instructions to run on some accumulated input value. As we accumulate our results, we keep track of our accumulator variable, which will be our result, as well as our original input, which can be pulled into later operations as well. I'll follow the conventions of the official Jelly tutorial and use the letter V to represent the accumulator, and omega to represent the original input. At the end of computation of a monadic chain, the value of the accumulator, V, will be returned. If a monad is encountered in the chain, it gets applied to the current accumulator, V. If a dyad-nilad pair or a nilad-dyad pair is encountered in the chain, the dyad is applied to the current accumulator, V, and the given nilad, with the order of arguments determined by the order of the pair. If a dyad appears without a companion nilad, it is applied with V on the left and the original input omega on the right. Finally, if a dyad is followed by a monad, then the monad is applied to omega, and the dyad is applied to V, and the result of the monad. These rules might seem arbitrary at a glance, but it turns out they're strictly a generalization of the fork rules we learned about in J. Specifically, a monad-dyad-monad chain in Jelly will be treated just like a monad-dyad-monad train in J. We haven't gone through the dyadic chain rules table since we won't be needing it, but note that it has similar rules to the monad table and is designed similarly to be a generalization of the J rules for the set. Remember that behind all the fancy words, all we're doing is taking a constant value, or nilad, and applying a bunch of operations, which we're calling monads, to it in sequence. Let's get started. We're writing our main program, which will be a niladic chain, so it needs to start with a nilad. Our nilad of choice will be the number 2. Now we want a list of all the numbers from 2 to 20 inclusive. The R dyad produces exactly this list, and one of our rules allows us to apply a dyad with a constant right-hand argument to our current value. Next, we want to calculate all of the prime factors. We'll start by using the AEF monad, which produces a list of pairs effectively in the same format as our baghash in Raku. The left hand of each pair is the relevant value, and the right hand is the number of times it occurs. Note that this AEF is 2 characters, but it's actually one operator. There's no function composition or adverbs happening here. It's just that one operator happens to have a name which is 2 characters long. Now we'll convert our baghash-like implementation into a list of elements. We'll do that like so. This requires some explanation. X is a dyad which repeats its left-hand argument some number of times, indicated by the right-hand argument, exactly like the double X operator in Raku. / works in Jelly exactly like it does in J. It takes a dyad and converts it to a monad that operates on a list, folding over the list. Since we're going to be applying these to pairs, or 2-element lists, X / has the effect of repeating the first element of a pair a number of times equal to the second element of the pair. The euro sign symbol is the for each quick. It takes an operator, a monad in our case, and applies it to each element of the list. We want to do our repeat fold operation for each prime number of each range element. So we want to go 2 layers deep, hence we apply for each twice. Now we have a list of lists of lists, and we want to flatten those inner lists so that we have a list of prime factorizations. Flatten in Jelly is done appropriately with the capital F operator, and we want to do it for each element. So we write this. Now we've got a list of lists of prime factors. Here's where we take our multiset union to perform the LCM operation. Multiset union is a dyad in Jelly, which is written with OE vertical bar. And we want to fold it over a list, so we append / onto the end. Finally, we have a list of the primes we need. Let's take a product, which is done with capital P. And we have our program. This solves Project Euler problem number 5 in Jelly. Tune in next time when we take on the 6th problem in hexagony. the hexagon-based programming language.